Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it, planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, NASA's chief scientist, and this is Gravity Assist. With me today is Dr. Alex Young from Goddard Space Flight Center. And Alex is a solar scientist, a physicist who's been studying the sun, its output, and what we call space weather his whole career. Welcome, Alex.
Oh, thank you. It's great to be here.
You know, what do we mean when we use that term space weather?
Well, space weather is this environment in the solar system that's created by the sun and the energy and matter that it puts out and how it interacts with all of the bodies in the solar system, the planets and everything else you can think of.
So it's like weather here on Earth. Things happen, and they happen. The wind blows over us, and there's wind in space, and so that's an interesting phenomenon. When you look out in space, you don't see that stuff.
That's right. And so we have this sort of somewhat steady wind that's coming off the sun. We call it the solar wind. And that's the sun's hot atmosphere, which is streaming out into space. It carries away the sun's magnetic field. And sometimes we even get these explosions and huge, almost like tsunamis that ride on top of the solar wind. And these are the more energetic phenomena that make up space weather.
So these are things like flares and coronal mass ejections.
Right. So the sun has a very strong magnetic field, and that magnetic field gets twisted up inside of it, much like the way rubber bands get twisted. They have tension, they have pressure, and sometimes they get twisted enough and they snap. They snap violently, releasing energy. A flash of light we call a solar flare through the whole electromagnetic spectrum. And sometimes they spit out these huge blobs of material and magnetic field. Those are called coronal mass ejections. And both of those can create shock waves that excite particles to near relativistic speeds. And so we get this storm of energetic particles.
You know, those are the kind of things, those particles you can't see, but they certainly can affect everything that we do from our instruments on our spacecraft, but also for human exploration, not only on station, but when we go beyond low Earth orbit.
Exactly. And they are creating this very, very dynamic but hazardous and hostile environment for humans out in space, but as well all of our technology, because all this stuff is electromagnetic. And so it interacts with technology, which is electric in nature.
Alex, what's the worst solar flare you've ever seen from the missions you've been involved in?
Well, the biggest one that I know of, and it actually happens to be the biggest one that was ever recorded in the space age, happened during a time period of about 2 weeks, end of October, beginning of November, we call the Halloween storms in 2003. And one of those flares that occurred just as the flaring region was rotating out of view on November 4th, created, we call it X-class flare. And this one was off the charts. It was bigger than anything we'd ever seen. And in fact, our instruments couldn't even record it. So we had to estimate how big it really was.
So when these flares take off and they start accelerating particles, does that happen in all directions, or is it very directional?
Well, flares, the light itself is not directional. It's pretty isotropic. So, I mean, if you see it anywhere that region is visible in the sun, you will see it. But the particles, those are very directional. They are created by jets, and that's actually those particles are actually slamming into the sun, creating the light, and then they're streaming out into space. But those are very focused.
You know, that other phenomena you mentioned, that coronal mass ejection, what's the worst CME you've ever seen?
Well, the worst CME I've ever seen happens to be, again, the biggest one we've seen in the space age. On July 2012, we had an event. It happened on the side of the sun, and it was caught by one of our other spacecraft, Stereo, which are in fact orbiting the sun. They're not looking from the Earth-facing direction. And we measured this at a phenomenal 3,500 kilometers per second. That sounds like a lot. And it's especially a lot for CMEs. It's the biggest, fastest one we've ever recorded.
So these are bubbles of reconnected magnetic field, and in those bubbles are all the atmosphere that it captures, and it just sort of lifts off and then flies at us.
Exactly. And the crazy thing is that they're really huge. They start off bigger than many Earths in size, and they quickly expand as they're moving away from the sun. And very quickly, they can fill huge portions of the inner solar system.
90 degrees or 100 or 120 degrees in size as they pass by the Earth.
Yeah, they're just phenomenal. And they're carrying all of that material, billions of tons of material, as well as the magnetic field of the sun inside of it.
So, as a young researcher in my particular field, that's where I take over. And we found that, when those coronal mass ejections hit the Earth's magnetic field, we always see aurora. Now, CME may or may not hit the Earth, but when they do, we're in for a beautiful, dazzling display of auroral lights.
And it's amazing, and that's the first sign that we can visually see and experience of what's happening. But there's so much more that happens when all of that stuff is interacting with the magnetic field and this kind of tear-shaped bubble around the Earth we call the magnetosphere.
So as you were talking, it comes to mind, over the space era, the 40, 50, 60 years now, where we've been putting these puzzles together and trying to understand space weather and getting a bigger picture of it. Have we seen everything the sun can put out in space weather?
Most definitely not. And, we think about it, we have seen not even a blink of an eye of the life of the sun. So much has been happening. The sun when it was younger, it was far more active, and we've really only seen a little bit. We know from looking at historical records, both things that humans have recorded in terms of aurora they've seen, that there are huge storms, but we also see signatures in radioactive elements, carbon-12, beryllium-10. These are things that are left by nuclear reactions in the atmosphere with particles. And we can see these traces in things like ice cores and tree rings. And we know there have been much bigger events in the past.
What are some of the big historic events that we've been studying?
Well, there have been a few in the modern age and space age. The one that I talked about, the whole series during October, November 2003, Halloween storms. A very famous one, 1989, March. That was when there was actually a storm that caused a power outage in Quebec. Very well known. But the big one that most people try to refer to is what's called the Carrington event. And that was seen by Richard Carrington in England in September, the end of August, beginning of September, 1859. There were a series of events, and he saw the first white light flare. So a solar flare visible in white light with a telescope from a sunspot. And then a few days later, they observed aurora here on Earth. And that's the first time they made the connection between these magnetic eruptions on the sun, the flare, and something occurring here at Earth.
Yeah, actually, scientifically, one would think that is the start of the beginning of understanding some aspects of space weather. So Carrington was an astronomer at night, and during the day, he sketched sunspots. And how the story goes, as he was sketching the sunspot, it actually came out of focus for off and on, and he worked hard to try to focus it, couldn't get it focused. Then he realized, this is a real event I'm looking at.
Right.
So he ran all over the observatory looking for people to take him up to the telescope. But this was at 11:30. They were all at the lunch. And so, he had to discover it on his own. But fortunately, another astronomer also looking at the sun at the same spot saw it too.
Right. And so this is the beginning of the modern age of space weather. And it's still, to this day, the key event that everybody compares to when they talk about a big space weather event and the kinds of things that space weather can do.
Yeah. Now, one of the reasons for that is, as you mentioned, indeed, he saw the reconnection occurring just above the sunspot, and that's what the flare started to do, and then a coronal mass ejection lifted off. 17 hours later, there was the aurora. Now, coronal mass ejections take what? Like 80 hours typically to go from the sun.
Right.
And so 17 hours, this thing was really moving and it had an enormous amount of mass. And then the aurora was observed cutting right through the United States, through Mexico, and down into Central America. So pretty spectacular event.
And this was a really cool event for a lot of reasons, and we've seen similar things even with this July 2012 event. The speeds are comparable. That's about 17 hours for it to reach about the distance from the sun to the Earth.
Now, that one didn't hit the Earth.
That one didn't hit the Earth. That hit a spacecraft on the side of the Earth, stereo, but that spacecraft was at a distance that's about the same distance. But the other aspect was we also saw this effect of multiple events where one event kind of clears out the way and then the big one blasts through, and it's got this free reign to just sweep through the solar system and slam into the Earth in this case.
Yeah, so it's a double whammy. It's really two coronal mass ejections. Those regions are so active that they continually reconnect. Now, they come from really big sunspots.
Right. We're talking sunspots that are many times the size of the Earth. And these sunspots, the bigger they get, the more complex they get. We can see how much energy they have contained inside of them. That gives us an indication of what sort of activity might we see.
So are there other events like the Carrington that we can go even further back?
We can, and there's been one that's been talked about recently. It's now called the Charlemagne event by some because it's estimated to be within a period of about 774 or 775, somewhere in that period during the time of Charlemagne. It was first recorded in carbon-14 in tree rings.
Wow.
Now, the original estimate was that this event was 1,000 times the Carrington event.
Wow.
But then this was put out by a group from Japan. But then some other scientists sat back and tried to figure this out. And they said, something doesn't seem right here. This is just a little bit odd. So they looked at their calculations, realized that they didn't calculate for a very focused particle event, and they treated it as kind of a giant bubble around the entire sun. And turns out it wasn't 1,000 times bigger, but it's still 10 to 20 times bigger than the Carrington event. And that's just massive.
Well, what would happen to our technologies today if an event like that occurred?
Well, it could be quite catastrophic. And there have been studies by the National Academies, estimates certainly billions and billions of dollars of damage, estimates up to even trillions of dollars, because it would have such a global impact on our technology infrastructure. We could see power outages across the globe in interconnected power grids especially. There would also be impact to communications, but another aspect, satellites. We would possibly lose many satellites.
Yeah, so the modern day technologies are kind of susceptible to these space weather effects.
And one of the aspects about this is that we are now in an age with technology we didn't have even during 2003, and certainly not during 1989. We've been in a relatively small solar cycle. That's the 11-year activity cycle. So we actually don't really know what a massive or strong solar event would do to the infrastructure that we have today.
So now that we know about this and we're becoming much more aware of how active the sun could be because it has been more active in the past, how can we protect our technology here on Earth?
Well, there are a lot of things we can do. One is simply prediction, that is trying to make some sort of estimate of when an event is going to occur. Now, as you mentioned, CMEs, they take some time to get here. Now, as far as a solar flare, there's not a lot you can do. Once you see it, it's here. So there you just have to be prepared for fast reaction time, knowing that you have a spacecraft, there's activity on the sun, and what kind of adjustments can you make to the spacecraft flight and flight controls. So we're studying things like drag and whatnot to better understand that. But the other things we can do is when we talk about the impact on the power grids, We can improve the power grids themselves, improve the infrastructure, and even when we know an event is coming, we can do simple things like basically turning the power grid off for a short amount of time, what we call a brownout. It's just like if you knew there was a lightning storm coming to your house, the first thing you might do is unplug your stereo.
Right. In fact, how it affects our power grids is really because of the aurora. The aurora has huge currents that are in the ionosphere, and so as they pass overhead, they induce other currents in our power grid that aren't usually there, and therefore they can overload the transformers, burn them up, and that's what causes the massive power outages.
Exactly, because these currents are looking for places to travel through, large conductors. And, we also see not just this happening in power lines, but we even see these large currents conducting through pipelines.
Yeah, right,
pipelines. That can actually cause corrosion to increase in the pipelines.
So as we talked about these massive coronal mass ejections that occur, sometimes they hit the Earth, sometimes they don't. But we've got other planets out there.
That's right.
So what happens to them?
Well, they definitely interact with all the bodies in the solar system, and they have had impact over the years. We now have had a mission called MAVEN, which has been studying Mars for a long time, looking at atmospheric loss. And we believe that over billions of years, solar wind and coronal mass ejections have slowly stripped away the atmosphere. And the atmosphere we see today on Mars is not the atmosphere it used to have.
Right.
But the other aspect is, what is the magnetic field of those different planets? Some planets like Mars don't have a magnetic field, a global magnetic field right now. Venus, in addition. So the kind of magnetic field determines the interaction that's going to occur, but it definitely occurs with all of the bodies in the solar system.
Do you think there's a little bit of connection with space weather and the importance for the formation of life in our solar system?
Absolutely. One of the things we know is the sun has changed over time. It was much dimmer in the past. It was spinning much faster, but it was also much more active. We estimate the early sun was producing many Carrington-like events on a daily basis.
Wow.
But also the spectrum of that star was different. We get much more UV, much more X-rays. So all of the planets were being bathed by huge amounts of radiation, and this has had an impact on how atmospheres themselves formed. This radiation is interacting with these atmospheres, changing how they evolve, and it could have had an impact on the energy source itself needed to spark life. Because, as I mentioned, the sun was dimmer, and we have what's called the young sun paradox. So did we have enough light, enough energy to support life? But there are other energy sources, the particles, not just visible light, but the X-ray and UV. So these are all pieces of the puzzle that we have to take into effect.
Yeah, so the faint young sun, means that it was very dim in its past. And that paradox, what that's all about, of course, is we know early on that Venus, Earth, and Mars had an enormous amount of water. And yet it had so much energy from other sources than just the visible light.
Right. And the cool thing is, we've always talked about the Goldilocks zone, this region where it's not too hot, it's not too cold, thinking in terms of liquid water. But what all of this research has now shown us is that whole idea of what is it to be habitable is much more complex. And we have to understand the activity of the star and all the other energy sources that it's producing to really define what we mean by habitability for our planets in our solar system as well as exoplanets.
Yeah, so the study of space weather's got to factor in. And so that is all about an evolution of the central star. So as you mentioned, our star, the sun, was rotating much faster in the past. It was dimmer, but all kinds of other things were going on. How is it going to continue to evolve? What is the next steps?
Well, it will continue on the course that it's on right now for quite a while, but eventually, inside the sun, its currently using as its fuel source hydrogen, which it's turning into helium. Eventually, once it uses all that up, it'll turn to the helium and start fusing it. And it works its way up the periodic table to a point where it can't fuse any more elements. And at that point, it starts to change. Its outer atmosphere starts to expand. It shifts more and more towards a red star, much like the star of Superman in Krypton.
Okay.
And it becomes what we call a red giant, and it starts to fill the inner solar system.
We know about these because we can see stars that are like that, as you describe, red giants and other evolved stars that have about the mass of our own sun. So it's got to be connected. It's a normal process of the evolution, and now we have computer codes that actually calculate that over time.
Exactly. I mean, all of this is the coolest thing about it is just recognizing that we are living in such a small little period, a snapshot of what's going on. And as we understand how the planets have evolved, we have to understand how the stars evolved and connect all those pieces over time.
You know, one of the things that I love to do when I talk to my colleagues is really try to understand how they got into this field. What was the events in their life that really got them excited about their science, gave them that gravity assist that propelled them forward to become the scientists they are today? So, Alex, what's your gravity assist?
Well, it's a multi-part assist. It's a couple of little tiny pushes and then one giant push. I started off, when I was a young kid, I saw the original Star Trek, not in syndication, and I was fascinated by this idea of exploring space, and especially the character Mr. Spock, the scientist on the Enterprise. And so I thought, man, this would be so cool to be able to do that. And then not around the same time, I saw a show by Carl Sagan called Cosmos, and he took you around the universe in a spaceship. He had his own spaceship and he explored, and I started to see, hey, I can actually do this. I can actually be an explorer like Mr. Spock, but I can do it in real life and study the universe from here with telescopes and spacecraft. And it was an exciting time because it was the early 80s. So Voyager results were coming out. I was writing to NASA. They were sending me pictures from Jupiter and Saturn.
Cool.
And at the same time, I was getting specs for the space shuttle. And we were just beginning with the launch of that. So all this was happening. And as I slowly slipped into high school, at that time, my dad was an art professor and one of his colleagues was a physics professor. And they made a deal. The physics professor's daughter wanted to study art and I wanted to study physics. So they said, if we can swap and in the afternoons go and meet with each other and learn. So I went and met with a physicist while his daughter met with my dad.
Wow.
And I learned about physics. He helped me and I built a laser and went to the science fair and really got into all of this. And so all of it just sort of came together finally. And that was the piece that just shot me out. And that was the really, really serious assist.
That's fantastic. Well, Alex, I really enjoyed our time today talking about the sun, certainly one of my favorite subjects. And really appreciate you here giving us your wisdom and letting us know what's happening in the field today.
Well, thank you. And I am so excited that you had me here. This was fantastic.
Join us next time as we continue our exploration of NASA science. I'm Jim Green, and this is your Gravity Assist.